Okay, we're going to delve deeper into rotational motion today. We're going to learn about torque and some conservation of energy. So, here's a quick reminder of all of the rotational quantities we've studied so far. There's the constant acceleration equations, which relate angular velocity to angular acceleration to angular position, very similar to the linear versions. Here's the relationship in terms of derivatives, right? Angular velocity is the derivative of angular position. Angular acceleration is the derivative of angular velocity. Here's the kinetic energy in terms of this idea we introduced last time, rotational inertia, which is kind of like the rotational version of mass. And the parallel axis theorem for finding the rotational inertia of an object around different axes if you know the rotational inertia of the object around its center of mass. And here's sort of a set of moments of inertia for various objects around an axis, most of them through the center of mass. We will be using this one a lot. No, not that one, sorry. We'll be using this one a lot. Rotation of basically a disk. The length doesn't matter, it's just the radius and the mass is 1/2 mr squared. So let's consider now if we have a stop sign and we want to exert a force on it, but we're going to add a pivot point. So right here, this point here, we're going to like drive a nail through it, and that's going to become the pivot point. And it's going to hold it in place, and the thing is free to spin around that point. So if I exert a force in this direction right here on it, let's say I exert a force here and it's pinned at that point, then what's going to happen is this thing here is going to rotate clockwise, right? Or not counterclockwise, it's going to rotate counterclockwise. Counterclockwise, which I will usually represent with CCW. And if I were to, instead of exerting the force there, I would exert the force at the same location but in the opposite direction, then it would rotate it in the other direction, and that would be clockwise, which I will represent with CW. And if you think about it, if I were to exert a force here at the same location but in that direction, then you notice that's not going to push it left or right. It's not going to turn it one way or the other. Here there will be no rotation in this case. Right? So the rotation is only happening when there's something pushing it one way or the other. If we were to look here, a couple other examples. So let's have our pivot point again, like so. And I were to exert, instead of, let's say at first I were to exert a force here at this point here. Force at that location, and let's say it was very far out, that's going to give it a rotation clockwise. And if I were to instead do F2, same magnitude but different location here, what's going to happen? Well, it's the same force, but this one here is making it turn more because it's further out, and it's with the same force you're pushing this here and rotating this around this point, and you're going to have twice as much rotational force, is what we call it, or torque, right? When you have a wrench and a nut, something like this, if you want to turn the nut, you want to push it here, you'll get a much better, you'll much more easily be able to spin it than if I push it here. The further out it is, the stronger the force is, and that's what we're going to call the torque, right? Is that rotational version of the force. Another point is if I were to exert the force right at the pivot point in any direction, right? It's not going to rotate it because it has to rotate around that point. So if I exert the force on the sign at that point, there's going to be no rotation. It's just going to sit there. Now, one last important example. Let's say I want to exert a force right here, a certain distance from the pivot point. And let's say I exert the force at some angle like this. Well, it turns out that the only, you can break it into two components. You can break it into the component of that force here that is perpendicular to the line, or you can draw it here. You can find the force that is parallel to the line. So here's the force parallel to the line. So I can break that into its two components. Based on this angle, I can calculate, the perpendicular and the parallel component. And it turns out this force here will exert no torque. It's just going to sort of pull on this pivot point. It won't do anything. But the component perpendicular to it is going to make it rotate, in this case clockwise. So for torque, it turns out that it's only the perpendicular component that matters. It's the perpendicular component of the force, perpendicular to, and by perpendicular I mean perpendicular to a line from the pivot point to the point where I'm applying the force. So this is the force that matters for the torque. So for torque, only the perpendicular component matters. And so if we want to sort of define the torque specifically, here's my pivot point, here's the point P where I apply the force F to get the component here that's perpendicular, right? This is the perpendicular component, which will be the same as this here, right? That's to be the same component. So here's the F perpendicular. So that'll just be F times sine of that angle, sine phi. So we're going to define the torque as being the perpendicular component of the force times the distance to the pivot point, because the further out you exert the force, the stronger the torque is going to be, and the more perpendicular component you have, the stronger the force is going to be. So F perpendicular times R, or FR sine theta. We're going to rewrite this as a cross product later on, but for now, this is good. So just as a simple example, let's calculate the torque in this case here. So I'm applying a 25 Newton force at that corner there, and we have a pivot point down here in the corner, right? And the distance, we'll say R is 2 meters long. So if I wanted to calculate the torque, represented by the letter tau, it's going to be FR sine theta. And so the force is 25 newtons, right? R is 2 meters. We'll put in sig figs at the end. And sine theta is the sine of that angle, 30 degrees. Remember, the angle has to be the angle that the force makes with the line here coming from the pivot point. And when I plug everything in, I get 25 times 2 times 30, so I end up with sine of 30 is a half, so I end up with 25 Newton meters. So that is the torque in that case. Let's just do a second example real quick. If I want to do, let's say, a force in this direction here, and let's say this one is 25 newtons, and I want to do a pivot around that point. And let's say that this angle here again is 30 degrees, right? So in this case, the torque in this case will be FR sine of 30 degrees, and let's call this distance here half a meter. So it's the same force, the same angle, but because it's closer, it's going to be less torque, and it ends up being 6.25 Newton meters. So we get less torque in that second situation because the same force at the same angle is closer to the pivot point. Let's do one more. This is to sort of help us establish the sign. Right now, I've been putting a sign on the torque, whether or not it's positive or negative, but that's actually important that we need to include it. We're going to define counterclockwise torque as positive. Okay, so that means when the torque is making it spin against the clock, it's positive. Why it was chosen that way, I don't know. That's the way it is. So here we have 100 Newton force applied a certain distance from the Mona Lisa's hand, I guess. And so let's call this 1 meter. I don't think the Mona Lisa is that big, but let's not worry about that. So we can calculate the torque, and you notice that this torque here would try to make it rotate counterclockwise. So we're going to make this a positive force, right? So the torque will be F times R times the sine of the angle. So it'll be 100 newtons times a distance of 1 meter times the sine of 45 degrees. When you plug it in, it works out to about 70.7 Newton meters. And we're going to leave it positive because it is counterclockwise. But let's say, let's do another part. Let's say this here is also 1 meter, and the force here is, let's make the force in this case blue, and the force here is in that direction. Let's make it also 100 newtons. Let's make it also this angle here, 45 degrees. So this case here, the force is going to make it try to turn clockwise. So that means this torque is negative by our definition. So our torque here will be minus the force times r times the sine of theta. And so that works out to be minus 70.7 Newton meters. Okay? So in one case the torque is positive here because it's pushing it counterclockwise. In the other case it's negative because it's pushing it clockwise. Here's another example. This one's from your textbook. We have a body here. It's pivoting around the point O in the middle there, and there are two forces acting on it. One is 4.2 newtons at a distance 1.3 meters, and the other is 4.9 newtons at a distance of 2.15 meters, and they have different angles. Theta 1 75, theta 2 is 60. And what is the net torque around this pivot point? Well, let's write down everything we know first, and then we'll calculate the pivot point. So the force 1 is 4.20 newtons, and it is a distance of 1.30 meters from the pivot point, and it's making an angle theta 1 of 75 degrees. And then there's force 2, right, which is 4.90 newtons. R2 is 2.15 meters, and theta 2 is 60 degrees. So the torque is going to be, the net torque is going to be the sum of those two torques, right? It's going to be torque 1 plus torque 2. And you notice that one torque is making it spin clockwise and the other one is making it spin counterclockwise. Let's have a quick look at that. This torque here is pushing it in this direction, which is clockwise. So this one will be negative. Whereas this torque here is trying to spin it counterclockwise. This one will be positive. So let's plug everything in and make sure we get our signs right. So torque 1 is the one that is positive because it's trying to rotate it counterclockwise. So it's going to be F1 R1 sine theta 1. And torque 2 is going to be negative because it's spinning it clockwise. So it's going to be F2 R2 sine theta 2. So we start plugging everything in, right? We have 4.2 newtons times 1.3 meters. I'll put in the sig figs at the end, times the sine of 75 degrees, minus, here we have 4.9 newtons times 2.15 meters times the sine of 60 degrees. And when we calculate everything out, we end up with minus 3.85 Newton meters. So this is rotating if it's negative, then it's rotating clockwise. Does that make sense? Well, here F2 is a larger force and it's further out. This is a smaller force further in, so this one will dominate and it is negative. So that's consistent with what we expect. We're going to develop another rotational equivalent of an equation that we're familiar with. Net force is equal to ma. For linear motion, we know that one very well. Let's look at the situation where we have here is a rod with a mass on the end, and we're interested in the torque version of this. And so we are only interested then in the force that is going to be tangential to the ball here. So this is the force perpendicular or force tangential to the ball's motion as it's rotating around here. So this component of the force is what's going to be important for torque. So we want the tangential version. So force tangential equals mass times acceleration tangential. So the torque, instead of force tangential, it's going to be force times r. And since it's at 90 degrees, the sine of 90 degrees is 1. So the torque is force times r. And we just multiply the right side by r as well. We have MAR. We're going to plug in for angular acceleration. A is equal to the angular acceleration times r. And so now we have torque equals m times the angular acceleration times r squared. This mr squared is just the moment of inertia of this ball, a distance m from ball m, a distance r from the pivot point. So we now have that the torque is equal to the moment of inertia times alpha. Torque equals I alpha, which looks a lot like F equals ma, except the rotational version of it, right? The rotational version of force is torque. The rotational version of mass is moment of inertia, or rotational inertia. And the rotational version of acceleration is alpha. So let's look at some simple examples. So let's do an example here. It says this figure shows a uniform disk that can rotate around its center like a merry-go-round. It has a radius of 2 centimeters and a mass of 20 grams. It's initially at rest. Starting at time t equals 0, 2 forces are applied tangentially to it, so that at time 1.25 seconds, the disk has an angular velocity of 250 radians per second. So force 1 has a magnitude of 0.1 newtons. What is the magnitude of force 2? So we have 2 forces acting on this, and after 1.25 seconds, it's rotating at 250 radians per second. So it wants to find out what is the magnitude of F2 that makes this possible. Well, since it ends up with counterclockwise rotation, that means F2 must be stronger than F1. So when we get our answer, we expect F2 to be stronger than F1. They both have the same radius, right? Let's write down everything we know. We have the mass of our object, m. It's 20 grams. And that, we'll write that in kilograms, so that's 0.0200 kilograms. We have the radius is 2 centimeters. Let's write that as 0.0200 meters. We'll keep some sig figs in there for now. F1 is given. It's 0.100 newtons. And F2 is the one we're trying to find out. And we know that at T1 equals 1.25 seconds, so after 1.25 seconds of acceleration, the angular velocity is 250 radians per second, which we're assuming that it starts from rest. And to do this, we're going to need to find the acceleration, right? We're going to find the angular acceleration, and then from that, we're going to find we're going to use sum of the torques equals I alpha to get all of that. So we want to find F2. That's our first thing. And to find F2, we're also going to need alpha. So here's what we can do. We can say, well, W1 is going to be equal to the initial speed plus alpha t. Do you remember this? This is sort of the kinematics equation. And so we can get that W1, since it starts at rest, it's equal to 0 plus alpha times T1. So in other words, the angular acceleration is going to be, not W1, omega 1 divided by T1, or 250 radians per second divided by 1.25 seconds, which means that the acceleration ends up being 200 radians per second squared. So we have the acceleration of this thing, and now we can use that to find F2. And to find F2, we're going to use our new sum of the torques is equal to I alpha. So there's 2 torques. One's going to be positive, one's going to be negative. The one that's counterclockwise is going to be positive. So F2 is producing a counterclockwise torque, and F1 is producing a clockwise torque. So we can leave it like this. I alpha, like so. And now I'm going to plug in for T2. It's going to be R times F2. And T1 is R times F1. And that's equal to I alpha. And now I want to solve this for F2. That's what I need here, right? So let's see. I'm going to divide both sides by R. F2 minus F1 equals I alpha over R. So F2 is equal to F1 plus I alpha over R. So we have everything. We have F1, I, alpha, R. Well, I, just a quick note for I, we can calculate I. It's a disk, so it's 1/2 mr squared. And when you plug in the mass of 20 gram or 0.02 kilograms and the radius of 0.002 meters, you end up with 4.00 times 10 to the minus 6 kilograms meter squared. So now we have everything, and we can plug it into this equation, and what we get is 0.140 newtons. And you notice that this force is stronger than F1, which it must be because we ended up with a positive angular velocity. So everyone's happy. Another example. This is similar, right? We have a disc or a cylinder, so we know its moment of inertia is going to be 1/2 mr squared. And we have 4 forces acting on it. It says to find the magnitude and the direction of the angular acceleration of this cylinder, right? So to find the angular acceleration, we do the sum of the torques is equal to I alpha, and we solve for alpha to get the angular acceleration. Well, let's just straight up calculate each of the torques. So torque 1 is going to be F1 times R, because it's a distance. You notice that F1 right here is a distance R. It's right on the rim, times the angle between F1 and R. So this here is 90 degrees, so it's times the sine of 90 degrees, which is just 1. Is that one going to be positive or negative? Well, if we look at it from the axis here, we see that it's rotating it counterclockwise. It's trying to make it rotate in this direction, so that's going to be positive. So we plug in a force. The force is given here. It's 6 newtons, and the radius is given as 12 centimeters. Let me write a little summary here. F1 is 6 newtons. F2 is 4 newtons. F3 is 2 newtons. F4 is 5 newtons. And big R, the radius of the cylinder, ends up being 12 centimeters, or 0.12 meters. And one of the forces is at radius little r right here, force 3. And that's only 5 centimeters. That's 0.050 meters. So when I plug in my values here, I get 0.72 Newton meters. Now, torque 2 is F2, and torque 2, you'll notice, is also a distance r away. It's also an angle of 90 degrees, right? This angle here is 90 degrees. And so when I plug in all the numbers, this time though, F2 is trying to rotate it clockwise, so that'll be negative. So we know it's negative that, so it ends up being negative 0.48 Newton meters. And if I go to torque 3, it's F3 times R. Now, the thing about F3 is it's not R, it's little r. And it's also trying to rotate it clockwise, so I'll put a minus sign there as well. And it's also 90 degrees, so it's sine of 90 degrees. So this ends up being minus 0.10 Newton meters, negative. For the fourth torque, the difference with this one is that it's F4 and it's R, but you'll notice that the fourth torque here is pointing in the same direction as R. So its angle is 180 degrees. So this is actually going to be a sine of 180 degrees, which is 0. This is not exerting any torque. So the net torque then, the sum of the torques, is going to be the sum of all 3 of those. And let me move that over a little bit. So the sum of the torques is the sum of all 4 of those, and we end up with the sum of the torques is 0.14 Newton meters. So the one positive torque overpowers the 2 negative torques. And we also need the moment of inertia. It's 1/2 mr squared for a cylinder. And that works out to 0.0144 kilograms meter squared. We now have everything we need to calculate our final answer. So, sum of the torques equals I alpha. We want to find the angular acceleration of this. So now alpha is going to be the sum of the torques over I. When I plug in my numbers, I get about 9.72 radians per second squared. So that's the angular acceleration of this cylinder with those 4 forces acting on it. Now let's look at an example here where we have a block hanging from a string from a cord that is wrapped around the rim of a disc. The block has mass little m, the disc has mass big M, and radius r. The mass is released and it pulls the string, making the disc spin. So we're going to assume no friction here. So now the difference here between this and what we've done before is this is no longer a massless disk. The pulley now has mass, and so it actually takes energy to get it going. So we need to include that when we do our total calculation. So let's write down everything we know real quick. The mass of the small hanging mass is 1.5 kilograms. The mass of the disk is 3 kilograms. The disk has a radius of 20 centimeters, so 0.200 meters, and the moment of inertia for a disk is 1/2 mr squared. Now, we can do this by doing sum of the torques equals 0, or sum of the torques equals I alpha, and by using sum of the forces in the y direction equals mass times acceleration. Okay, so what's happening here is, well, let's draw an extended body diagram for the sum of the torques one, right? We have the disk. So let's draw, we're saying that all the forces on the disk, here's the pivot point, all the torques on the disk are going to give it an angular acceleration, right? So here, what's the force downwards at this point here on the edge of the disk, where the disk has a radius r? Well, there's going to be some tension T downwards due to that string. And what's the acceleration going to be? Is it going to be positive or negative? Well, that's the only torque, by the way, on it. So it's the torque is trying to spin it clockwise, so the angular acceleration is going to be negative. So we say that sum of the torques is equal to minus I alpha, because it's trying to spin it clockwise. And so since there's only one torque, the torque is the torque due to the tension, and I'm calling it negative because that torque is trying to make it go clockwise. And so we now have an equation. I can plug in, so I'm going to simplify here. I'm going to cancel out those two negative signs, and the torque, remember, is just going to be tension times the radius, because the tension is the distance r from the pivot point, times the sine of 90 degrees, because it's a nice 90-degree angle, and this is just 1, right? And that's equal to I alpha. What's I? Well, I is 1/2 mr squared times alpha. Let's see. That cancels out one of the r's, and I can solve this for, and this is just, here, this sine theta is just 1. So I end up with torque equals 1/2 mr alpha. So we're trying to find angular acceleration, but we have the tension and the angular acceleration, so we still need to find what the tension is. Well, we can do the sum of the forces on the block. So this is for the block, right? I'm going to say the sum of the forces for the block. So let's draw a free body diagram for the block. There's going to be a force downwards on the block, mg, and there's going to be a tension upwards, right? I'm going to pick upwards to be positive. So sum of the forces is going to be equal, and I'm going to call it minus ma, because I know that the block is going to be accelerating downwards. So what are the two forces on the block? Well, there's the tension upwards minus the force of gravity downwards is equal to minus ma. So now we have two equations and two unknowns, right? We want to find the angular acceleration. So I'm just going to take this tension here and plug it into there and then solve for the acceleration. So let's do it then. So 1/2, I'm going to plug in 1/2 mr alpha for the tension minus mg equals minus ma. I want the angular acceleration. I'm going to replace a here with alpha r. I'm going to write a is always related to alpha. The angular acceleration is going to be related to the acceleration at that point. So now let's rewrite this. 1/2 mr alpha minus mg equals minus MAR. I'm going to collect all the alphas on the left-hand side. Like this, and move everything else to the right side, like so. I can factor out that alpha. And equal to mg. Solve for alpha. I can solve for alpha and do a little simplification. I end up with mg over 1/2 mr plus mr. And if I plug in all my values, I get an angular acceleration of 24.5 radians per second squared. So that is the angular acceleration as the block is pulling down and making that pulley spin. A 30 kilogram wheel, we're going to treat it as a thin hoop with a radius of 1 meter, is rotating at 300 revolutions per minute. It must be brought to a stop in 20 seconds. So how much work is needed to stop it? Well, work is equal to change in kinetic energy. So we just need to find the change in kinetic energy. Let's write down everything we know. So it's initially moving at 300 revolutions per minute. Well, we obviously want to change that to radians per second because that's the natural unit for this kind of thing. So 1 minute is 60 seconds, and 2 pi radians is 1 revolution. So you notice the minutes cancel out, the revolutions cancel out, and this becomes 10 pi radians per second. What else do we know? We have the initial mass. It's given as 30 kilograms, and we're given its radius. It's 1 meter. And the moment of inertia for a thin hoop, you look it up on the table, the moment of inertia for a thin hoop is just mr squared. All right? And so if you plug in the mass and r squared, you end up with 30 kilogram meters squared. So those are our knowns, and we want W final, of course, to be 0. So the work required to do this is going to be K final minus K initial. K final is 0 because it stops. It's at rest at the end. So we just end up with minus 1/2 I omega initial squared. And when I plug in everything, I get that I need to do about minus 14,800 joules worth of work to stop this wheel from turning. The next example I'd like to do is similar to the last one. It's 2 masses hanging from a pulley, one on either side, and they're connected by a rope, and they're released. This is a very famous problem in physics. It's called the Atwood problem. No relation to famed Canadian author and poet Margaret Atwood, but it is a cool problem. So we have mass 1 on the left and mass 2 on the right. You notice that mass 2 is larger than mass 1, and what's going to happen is when you let it go, mass 2 is going to go down, mass 1 is going to go up, and the wheel will spin, okay, and the pulley will spin, and everything has a mass, so we have to take into account the torques on this pulley. So there's 3 things we need here to find the acceleration of the blocks. We want to find how fast they're accelerating up and down. So let's start by looking at a free body diagram for M1. So if I look at M1 and I draw a free body diagram, there will be here some force of gravity downwards, right? M1G. And there will be some tension upwards. So let's call it T1. And I drew T1 slightly longer than mg because I know that the block is going to accelerate upwards. For the pulley in the middle, right? The pulley, capital M, let's draw an extended body diagram. We need extended body diagrams for things like this. So for this pulley here, I have a pulley that has a radius r, and there's going to be, and this is also R, of course, there's going to be two torques around the pivot point. There's going to be one due to tension 1, and there's going to be one due to tension 2, which I'm going to draw slightly larger because I know that one's going to be stronger. Right? And so that's due to the pulley. And the third one, of course, is going to be due to mass 2. So M2 will also have a free body diagram, and it will be M2G, and then there will be some tension upwards, but M2, the force downwards, will be larger because it's accelerating downwards. So let's quickly write down the equations for each of these things. So for M1, it's the sum of the forces in the y direction, right, up and down, is equal to M1 times the acceleration. Now, should it be positive or negative acceleration? It's accelerating upwards, and we're going to assume the y-axis is pointing upwards is positive. So it's positive acceleration. So the two forces on M1 is the tension 2 to 1 minus M1G is equal to M1A. So we have an equation. Let's look at, for this one, it's the sum of the torques equals I alpha. Now, is it going to accelerate clockwise or counterclockwise? Well, M2 is larger, so it's going to pull harder, so it's going to rotate clockwise, which means we're going to take this to be negative. So I write down then what are the positive one. The positive torque is going to be the torque due to tension 1. And then the negative torque is going to be the torque due to tension 2. That's going to be equal to minus I alpha. And for our third equation, we have sum of the forces in the y direction is going to be equal to M2A. Now in this case, it's accelerating downwards, so we're going to make that negative. So what are the forces upwards? Well, that should be T2, shouldn't it? There'll be T2 upwards minus M2G downwards, due to gravity downwards, is equal to minus M2A. So basically, I want this acceleration. I want the acceleration, right? And you notice that I gave the same acceleration to M1 and M2. And I can also rewrite this in terms of acceleration. I'm going to write that as acceleration. The angular acceleration is the linear acceleration over r. So with these three equations, here's how I'm going to solve it. Basically, I just want to find the angular acceleration. Or I want to find, the acceleration A. So what I'm going to do is I'm going to solve this one for T1. So T1 here is M1 A plus M1G. And I'm going to solve this one for T2. It's equal to minus M2A plus M2G. Now I want to plug it into the equation. Oh wait, let me do one last step here. So the torque is going to be equal to tension 1 times the radius minus tension 2 times the radius is equal to minus IA over the radius. So I am now going to take this tension 1 here, plug it into here, take this tension 2 here, plug it into here, and solve for the acceleration. It's a bunch of math. Let's get started. So tension 1 is M1A plus M1G times R. So that's the first term minus, and I plug in tension 2, which is minus M2A plus M2G times R. And then the right hand side of that term is still minus IA over R. So now we know everything in here except A, and it's a bunch of steps. We want to solve this for A, and let's take my word for it, or you can try it on your own if you want to have some fun. It's going to be M2 minus M1 divided by M1 plus M2 plus capital M over 2. Okay, now what I did in here is I solved for A, and I also used the moment of inertia for the disk is 1/2 m r squared. So I solved for the acceleration of those two blocks for that particular situation. Now, when I plug in the numbers, what do I get? I get about 1.568 meters per second squared. So that's how fast the blocks are accelerating, one up and one downwards. And that is the Margaret Atwood machine. Next, I'd like to talk about conservation of energy. Well, just like before, right, we had the work kinetic energy theorem. Work is kinetic final minus kinetic initial. Work is the change in kinetic energy. That's true even if there's rotational kinetic energy. And just by our definition of work, also we show that work is the integral of force dx. We can also show that work is equal to the integral of the torque d theta from initial angle to final angle. So this is sort of a basic introduction to some of the conservation of energy principles. So let's see an example of what we can do with that. Let's say here I have, we're not going to do part B. Let's say here I have another mass hanging from a pulley, and that mass starts off here, and we let it go, and it goes down it falls down a certain distance. Okay, so we're told here that if R is 12 centimeters and the mass is 400 grams, the mass of the pulley is 400 grams, so 0.400 kilograms. The mass of the little block is 0.050 kilograms. And the block descends 50 centimeters. So in other words, if I have this block and I let it go and it goes down 50 centimeters, how fast is it going? I can use conservation of energy to figure that out. I just say E initial equals E final, just like conservation of energy that we did earlier. So E initial, at the very beginning when the block is just held there and before I release it, so we're assuming that the block starts at rest, right? And when it gets down here, it has some V final that we want to find. So let's say it has some initial kinetic energy plus some initial potential energy is equal to its final kinetic energy plus final potential energy. So initially nothing is moving, so there's no kinetic energy. So the kinetic energy is 0. And if we call this here, we're going to call this y equals 0. So initially it only has gravitational potential energy, mgh. And at the end, the block is moving and the disk is spinning. So there's going to be some rotational kinetic energy plus some regular translational kinetic energy and no potential energy because the block is at y equals 0. So now we have mgh plus 1/2 I omega squared plus 1/2 mv squared. So what I can do here is there's a relationship between omega, which is the rotational velocity, right? Omega is the relationship between omega and the velocity is just v over r. So I can plug that into here and write mgh equals 1/2. Now I it's a disk as usual, so what is I? So I, as usual, is 1/2 mr squared. I use that example too much. 1/2 mr squared plus, oh sorry, I forgot to plug in omega. So omega is v over r squared plus 1/2 mv squared. And I do a little simplification. I end up with mgh equals 1/4 mv squared plus 1/2 mv squared. Solve for v. Let's see. Mgh equals 1/4 m plus 1/2 m v squared. I solve that for v and I get the square root of mgh over 1/2 little m plus 1/4 big M. And when I plug in all my values there, I get about 1.4 meters per second. So conservation of energy problems, we'll do more of those a little bit later on.